All right, good morning, chemists. We'll get started. So we just had midterm 3 yesterday. And so the average was a 70%. Oh wow, yeah, it was really good. I was super happy about that. Just for comparison, when I taught this course last summer, the average was a 60%. Yeah, but that was when it was a beefier midterm. So super happy about those scores. So now my question for you is, I can release the grades. I checked over it, everything looks good. I just can't release the exam responses until next week. So my question is, I'll just ask you guys, do you want me to release exam scores after class? Yes? But you can't see the responses yet, is that okay? All right, then I will release it after class. Yay. Okay. All right. Yeah, so 70%, super happy about that. So let's keep up that motivation for midterm 3. We have a nice, not break next week, but there's no exam, but then there is one the following week for midterm 3. Okay, so let's continue on with chapter 16. We may or may not finish it today, not sure, but let's continue on. So we're still talking about big K, but just specifically for chemical equilibria happening in water. And so we talked about strong acid, strong base, pH calculations in the first part of the chapter. And so now we're going to move on to weak acid and weak bases. We can calculate the pHs of those, though, because they're weak acid, weak bases, they follow chemical equilibria. They have K values, so we have to use an ice table. But these ice table calculations are easier than in chapter 15. But all those same concepts from chapter 15 still apply here. Okay. So remember, with strong acids, we had the full forward arrow. That's why we were allowed to just assume if we had like a 1 molarity HCl solution, then we had 1 molarity H+, because it fully ionizes. But here, with weak acids, we have to follow a chemical equilibria, big K. So we use different expressions to represent weak acids and weak bases. Both of these reactions have a Kc associated with them, where C stands for concentration, but we're going to be hyper specific here and say for weak acid, typically you're given a Ka value, where A stands for acid, while a weak base, you're given a Kb value, which represents the base dissociation for that reaction. So let's look at a weak acid acting as a weak acid. Just like, a strong acid, if you put something like HF, HCl into water, we see that it ionizes into its cation and anion. So for here, HF is going to donate its proton, that's what Bronsted lauric acids do, to water, making a hydronium cation, which is basically the acidic part where we calculate pH, and F-, this is your conjugate base. But typically, again, chemists were lazy, so we don't want to write that water molecule in there. So oftentimes we'll simplify this expression to just HF dissociates into H+ and F-. But remember, H+ doesn't exist. It's always attached to a water molecule. Both of these expressions are exactly the same. It's just one is missing a water molecule. So we can write the Ka expression for this just like for any K expression. Products over reactants. Only things that are aqueous go into that K expression. So let's go ahead and do that, where we do products over reactants, and you'll see it's quite nice for acid and base equilibria. Do you see how all the stoichiometry is just 1 to 1 to 1? So we never have those dumb exponents that we forget about sometimes. So what's nice is everything is a 1-to-1 ratio. So when we do products over reactants, it's, let me do the top one first. So it would be hydronium cation. The other product is fluoride anion, that's the conjugate base, over the concentration of HF in this solution. So this K expression shows you, okay, what is the ratio of the ionized product and the intact molecule of a weak acid equilibrium. Because remember, we don't have full ionization, only some of those particles actually do ionize, where we still have some intact particles. So this value tells us the ratio of how much is it ionized, how much of it is still intact. So this expression is for that top one, but if you write it again for the simplified version. Notice how I didn't include that water molecule because it's a liquid. Only things that are aqueous or gases go into the K expression, so we don't use that water. So for the simplified version, you'll see that it's the exact same expression. It's just H plus instead, F minus over HF. You'll probably use this red form a lot more because it's, again, annoying to write that extra water molecule when you don't really have to. And so you can go to textbooks and look up the K value, the Ka value for this acid, HF, and you'll find it's about 6.8 times 10 to the negative 4. And of course, at a specific temperature, most of the time we're working at 25 degrees. So those values you see are at 25 degrees Celsius. So what you see is HF only ionizes a little bit. The K value is quite a small number, so it doesn't completely ionize. Okay, so that's for a weak acid. There's its K expression. Let's look at a weak base that has a Kb expression because B stands for base. So how weak bases differ is we have to write a different chemical reaction for a base acting as a base. Bronsted-Lowry acids donate protons. Bronsted-Lowry bases accept protons. So we have to write the expression or the reaction that shows that. So here is ammonia, our stereotypical weak base that we work with. It's like the simplest of them. When ammonia acts as a base, a Bronsted-Lowry base that accepts a proton, we actually need to write that water molecule there. Of course, this is dissolved in water. So for a weak base expression, you have to have this water molecule because ammonia accepts a proton. That proton has to come from somewhere. It's going to come from water. So what's going to happen is that lone pair on ammonia is going to grab one of the protons. It's going to rip one of the protons off of water, leaving behind hydroxide. So that's the rest of the water molecule. And then you're left with the conjugate acid, ammonium, where it gained that proton. So that is a weak base reaction. For any generic weak base will follow this exact same form. You take the weak base, you add a water, combine it with water. That base steals a proton from water, leaving behind hydroxide and the conjugate acid as your two products. So here, there's no other simplified way to write a weak base chemical reaction. So we can just go ahead and write this Kb expression doing products over reactants again. And so we see our products are NH4, the conjugate acid, times hydroxide concentration. Again, everything's a 1-to-1 ratio, very nice. And then on the bottom, we have ammonia. And a note, we do not include water in this expression because it is a liquid, even though it is in the chemical equation. So that is Ka, Kb. A stands for the reaction. It's representing the reaction of that thing acting as an acid. Kb, B stands for that thing is acting like a base. So those are different reactions. Ka and Kb are different reactions. So keep that in mind. Okay. So these Ka, Kb values, again, they're no different than the Kcs we talked about before. They're just specifically saying, is the thing acting like an acid or a base? You can find these numbers in textbooks, all right? You can look up, you can just Google what is the Kb of ammonia, and you'll find 1.8 times 10 to the negative 5. Those are annoying numbers to read, right? They're small numbers. No one likes to read those. So oftentimes in textbooks, you're going to find pKa values. All right, if you want to know how acidic or basic a weak acid or base is, oftentimes you'll find tables upon tables of pKa and pKb values because small numbers are annoying to read. And P, remember, is just a function. It just means negative log of that thing. So what we see here is a bunch of different weak acids. Here are their Ka values. Again, look how annoying those numbers are to read. So instead, you can represent that same number with a pKa value instead, where you just take the negative log of that Ka value. And so what we've learned here about that negative log, I guess, function or, mathematics is that the larger the Ka value, these are all small numbers, but a small negative sign to the exponent on 10 typically means a large number, while a large negative number in that exponents means a really, really small number because you're moving that decimal point a lot of places, is represented by the whole number in that pKa or pH value, where a pKa of 2 is actually a fairly large Ka value versus a pKa of like 9.9. That's a very, very small Ka value. So what we see here is that the magnitudes of Ka also tell us the relative strength of these acids. Large Ka values, oh, I guess it's down here. I have it down here, all right? A strong weak acid, so a weak acid that is fairly acidic, that donates a lot of its protons, typically has a large Ka value, right? While because Ka and pKa are related by that negative log function, what you'll see is a strong weak acid also has a small pKa value. So what you see here at the top of this table, we have strong weak acids, but on the bottom is fairly weak. These don't really donate their protons as much. They have very, very small Ka values. So our strongest acids have large Ka values, but small pKa values, closer in the acidic region. So like an example would be like if, Ka was 1 times 10 to the negative 2, that's a fairly large number in terms of K values. Its pKa would be a low number, 2. And of course, this is for pKa, pKbs you can also find as well, same idea, but you're looking at the base form. Okay, so those are our weak acids and weak bases. Remember we looked at this table earlier and we said, oh, stronger the acid, crappier its conjugate base. So in the previous section, we just kind of looked at it conceptually, but now I'll show you mathematically why that is, and it's because Ka and Kb are related to one another for an acid-base conjugate pair. So we'll look at the math of that. You know, if you really got along with this table, it'll make more sense once I show you the numbers. So now we're gonna dive into the numbers. It was slide 27, all right, where we are going to calculate pHs and use ICE tables for weak acid, weak base systems. But don't be scared. It's just like chapter 15, but honestly, it's easier because everything's a 1-to-1 ratio. And we almost 99.99% of the time can use an approximation if that's the kind of question it is. So these are the same types of ICE tables we did in chapter 15. There's 2 types. One where you never use an approximation. That's this first one we're going to do. It's what I call the Sudoku method, where in this type of question, when applied to a weak acid system, I typically give you the pH. All right, I give you the pH and I ask you to calculate K. This is just like what we did in chapter 15. All right, that I give you basically a hint at the equilibrium line so you can fill in the rest of that table, and then we can calculate Ka. Never make an approximation because I'm giving you X. I'm giving you the value of X, so just plug it into that ICE table. So we're using the exact same skills, but the idea here, and the big idea is whenever I give you a pH measurement, it always represents, it always describes what the H plus or OH minus concentration is at equilibrium. So whatever that pH value, that is your hint to the equilibrium line. And so I tell you here in this question that, okay, a student prepares a 0.1 molarity solution of a weak acid system, formic acid, whatever, and found its pH to be 2.38. That's going to be really useful to us because that's going to help us fill in the rest of that ICE table, that pH value. Calculate Ka for formic acid. This is just like the type 1 ICE tables back from chapter 15. I have one issue, one gripe with this question, and that is the language that's used to describe it. So as chemists, I really, and as scientists, I really hate the word found. All right, I hate that word because when you say like, oh, I found the pH, I found the mass, it sounds like you like lost it and you like found it in a drawer. All right, give yourself more credit. This student measured the pH. Doesn't that sound like, you know, fancier? Okay, give yourself credit. It's not found. They measured the pH to be, you know, 2.38. So give yourself more credit. Give your, you know, make your lab report or whatever sound fancier. You didn't find that data. It wasn't lost in a drawer. you measured it. So just be careful with your language, so you express what you're actually thinking about in trying to communicate to others. Okay, so use the word measured. Okay, so approaching this question, just like chapter 15, I tell you that this student prepared a 0.1 molarity solution of formic acid. So here's the equation for the Ka expression of formic acid. We want to use Ka because formic acid is a weak acid. So here I show you the actual chemical formula of formic acid, but you could also simply just simplify this as Ha breaks up into H plus and A minus. You can write it that way as well, because all weak acid systems follow the exact same type of dissociation. You start with your weak acid, HA, it dissociates into H plus and its conjugate base. So you could write it either way. So the idea here is that concentration is going to go into our initial line. All right, we're going to put that in as initial, and it's in concentration already. That's great because Ka and Kb are technically Kcs, so we want to use concentration. We're going to start with 0 of everything else. All right, so just like before, you think, which way does this reaction have to go? Forward, yes. So the change line, and this is where it's great. Look, all of the x's, it's just minus x plus x plus x, because everything is a 1-to-1-to-1 ratio. Fabulous. So just like before, we take the columns and add them up. At equilibrium, you're going to lose a little bit of that intact weak acid. So it's going to be 0.1 minus x. So some of that breaks up, and that's because you create some H plus, that acid, and you create your conjugate base x, an x amount of that conjugate base. All right? And so just like all ice tables, you take that E line and you shove it into the Ka expression. You can go ahead and just use a generic one where you have your H plus times A minus over HA. Right? That means the same thing as what's written here. You're going to be writing these, all Ka expressions look exactly the same, so just writing it this way helps save you some time. And so there we go. We have our products over reactants, so then we can go ahead and plug those in and get that Ka equals x squared over 0.1 minus x. Right? So this question, remember what's being asked. I'm not asking you to calculate x. I'm asking you to calculate Ka. So the last bit of information that we didn't use is the pH, all right? So I give you that the pH equals 2.38. And so remember what pH represents. It's just the negative log representation of H plus concentration. So if I give you the pH, you actually also know the H plus concentration at equilibrium. It is 10 to the negative 2.38. All right, and so if you plug that into your calculator, you get that the H plus concentration is a small number, 0.00417 molarity. H plus. That number, that H plus concentration is X. That's X. So you can just go ahead and shove that number back in to your equilibrium line. All right, and that's the value of X, so you can just put it into that Ka expression and then calculate what K is from there. So that pH value is your hint to the equilibrium line. It tells you what X is specifically. And so should I make an approximation here? Should I get rid of that minus X? No, because you know what X is. If you make an approximation right now, you're just being lazy. All right, you know what X is, just plug it in. So let's do that. So Ka equals 0.00419, or 7, whatever, squared over 0.1 minus 0.00417. There we go. All right, and so that's Ka. Don't forget the square up top because it's x squared. And so you get that the Ka value is something like 1.8 times 10 to the negative 4. And that's a normal Ka value. You'll see, like if you got a Ka of like 500, you shouldn't see numbers like that. You'll be interacting with enough K values to know what is a reasonable number. And that sounds reasonable, 1 times 10 to the negative 4. All right, so that's a type 1 ice table. So now let's move on to a type 2 ice table. This time, I'm giving you Ka, and I want you to tell me the pH of this solution. So again, what we need for this ice table, you always need the balanced equation and the K expression. Then you can build your ice table, plug in your known values. So the full question is, what is the pH at 25 degrees Celsius of a 0.3 acetic acid solution and its percent ionization? We'll do that one last. We'll do the pH first. But the idea here is let's calculate pH. I give you the Ka value. All right. So I didn't give you the balanced chemical equation, but because acetic acid is an acid, we're going to use a Ka expression. All weak acids follow the same dissociation, the same chemical reaction. So acetic acid is written this way, CH3COOH, but you can simply just call it HA. All weak acids are basically HA, H plus attached to a conjugate base. So let's just call that thing HA. So when a weak acid dissociates, you start with HA aqueous and it breaks up into H plus and A minus partially. Those two are aqueous as well. I just forgot to write it. All right. The Ka for this chemical reaction is simply H plus times A minus over HA, just like the previous one. It's just different. We're working with the ice table a little bit differently. So now that we have the balanced equation, we start filling in our ice table. I give you a concentration, so it's 0.3 molarity. We have 0 of the other things. Hopefully this feels familiar. Even from chapter 15, this reaction must go forward. So the change line is minus x plus x plus x. Fill in those or add up those columns. So at equilibrium, you lose a little bit of HA, so 0.3 minus x. You have an x amount of H plus and an x amount of A minus. So this looks literally exactly like our previous ice table, but the difference is I give you Ka. We need to figure out what that H plus concentration is to figure out what the pH is. All right, the pH of the solution. We can't just say, oh, the H plus concentration is 0.3 molarity. No, we can't say that because acetic acid only partially dissociates. Only some of it becomes H plus. If this was 0.3 molarity HCl, yes, all of it dissociates, but this weak acid follows a chemical equilibrium. So it looks like we need to solve for what is X. X actually is the H plus concentration at equilibrium, and that's the piece of information we need to calculate pH. So essentially, here you see we are solving for X, and that's the typical type 2 ice table that we work with. So just like before, we want to plug those equilibrium concentrations into our Ka expression. So Ka equals x squared over 0.3 minus x, but this time I've given you Ka. It's 1.8 times 10 to the negative 5. So there is an expression that technically we can solve. As written, it requires the quadratic formula, but do you want to use the quadratic formula? Nah. So what are we going to do? What are we going to do? We're going to get rid of that minus x on the bottom, right? So getting rid of that minus x, we know that that x is going to be a very, very, very small number compared to the 0.3 that it's being subtracted from. And so if x is a really, really small number, if you actually did do the minus x there, you're not actually changing 0.3 in the denominator that much. So here we've really simplified the math. It no longer requires the quadratic. It's just simply a square root. So to get x, it is equal to 1.8 times 10 to the negative 5 times 0.3, take the square root of all of that. And so when you get that x is equal to 0.00232 molarity. All right, so that's x, molarity, but it's the molarity of what? Look back at your ice table. Oh, it's the concentration of H+. Perfect. That's exactly what we need to calculate pH, because if you just take the negative log of that number, you get that the pH is equal to 2.64. All right. So here we go. That's your ice table for a weak acid solution. 99.999% of the time in this class, you will just make the approximation and get rid of that minus x on the bottom. So they're not that bad of calculations. All right, but again, the full, chemical equation here and the ice table tells you that there is that minus x. What we get is that x, yes, is in fact a very, very small number. That doesn't really change the 0.3 that it's being subtracted from, right? So there's the pH, but then the last way that I can ask you to express this type of question is percent ionization. So percent ionization is just a metric of understanding how much of this weak acid dissociates into ions. So here is the equation for percent ionization. I do give this to you on the exam, but what we want to do to kind of further characterize this solution is take that H+ concentration at equilibrium and divide it by how much acid we started with initially, multiply by 100, and you're essentially calculating how much of that acid dissociates into ions. So percent ionization in this question is equal to essentially X, because H+ is the concentration, or X is the concentration of H+ at equilibrium, over how much HA we started with initially. So in this question, it's going to be that 0.00232 molarity number we got over 0.3 molarity. That's how much acid we started with, times 100, and you get that this solution is 0.77% ionized, so even less than 1% ionized. And so what we see here, when we thought about approximations and the 5% rule, usually this approximation we use where we get rid of that minus x is only really valid if that percent ionization stays below 5%. Basically, we're saying, less than 5% of our sample is becoming H+. So we can go ahead and just get rid of it in the denominator there. All right, so we got 0.77%. So less than 1% ionized, this solution is fine to make that approximation. So both of these calculations, pH, percent ionization, you have all the information to calculate both of those. Okay. All right, let's do another one. Okay, so here, given Ka initial concentration. So this is another type 2 ice table where we are calculating X because we want to calculate the pH. pH comes from the ice table and solving X. So this time, what is the pH of benzoic acid? And I give you the Ka. Do I really need to know what the formula of benzoic acid is? Now, I can just call it what? HA. Yes, all weak acids are just H+ attached to something else, some conjugate base. So I'm just going to call benzoic acid HA. So when HA, a weak acid, acts like an acid, it donates a proton and also leaves behind its conjugate base. So we write out our ice table. Very similar to the previous one. Actually, it's the exact same. It's just different concentrations, different K value. And so the pH of this weak acid is take the initial concentration, 0.15 molarity, 0 of everything else. We're going to move forward, so we're going to shift forward, so consume some HA, gain some H+, gain some A-. So at equilibrium, we have 0.15 minus X of HA, X amount of H+, X amount of A-. Hopefully the third time's the charm, where we see, oh yes, Ka, the Ka expression is, for any weak acid, is H+ times A- concentration over HA. Products over reactants, shove in your equilibrium line into that expression. So Ka equals X squared over 0.15 minus X. I give you Ka for this acid. It is equal to 6.3 times 10 to the negative 5. You can solve this, but I'm going to just be lazy and use the approximation again, all right? So see how this question is literally no different than the previous one. The only thing that changed was the initial concentration that's at the bottom in the denominator in our Ka expression and the value of Ka. So really, once you do like 5 of these, you realize that this pH calculation always ends up looking the exact same. So you don't actually have to do an ice table every single time. I encourage you to do it for the first 5 to 10 that you do, but you'll see the process. You'll understand that process and be able to skip a lot of that ice table step. So I'm going to be lazy and not do the quadratic formula, so I'm just going to approximate and get rid of that minus x on the bottom. So then this just becomes x squared over 0.15, that initial concentration, equal to Ka, 6.3 times 10 to the negative 5. So it's just a square root. Beautiful. And so when you solve for x, take the square root of those two numbers multiplied by one another, you get that x is equal to 0.00307 molarity. X represents the concentration of what? H+, yes, perfect. And that's exactly what we need to calculate the pH. So just take the negative log and you get that the pH is 2.5, right? Looking at sig figs, because I've been ignoring them a little bit, the Ka value has 2 sig figs, so really our X value should only have 2 sig figs, so that's why you see the pH value only has 2 decimal places, right? Because all of this is multiplication. All right, so that's the pH value. Once you calculate what X is, and then just to finish this off, percent ionization for this solution is going to be X divided by the initial concentration of this acid. So the X value we just got is 0.00307 over the initial HA acid concentration, so 0.15 times 100. And so you see that this solution is 2% ionized, right? Okay, perfect. So those are our weak acid pH calculations. They're not that bad. Honestly, I think chapter 15 is harder because all of these are just 1-to-1-to-1 ratios, and they basically always shift in that forward direction. It's just once we calculate X, we just manipulate it a little bit to actually show it as a pH value because those H+ concentrations are really small and annoying to read. All right, so that is our weak acid equation. So these 3 questions all looked at what's called a monoprotic acid. Monoprotic means there's only one proton to donate. So now we'll look at polyprotic acid. Polyprotic acids, these are acids that have more than one proton that can be donated. So the detail about weak acids is that if you have a polyprotic acid, so in some examples, H2A, H3A, notice how there's 2 protons or 3 protons that can be donated. The idea here is that each of those protons, those acidic protons, are only donated one at a time. If you put H2A into solution, both protons don't pop off at the same time. They get donated one at a time. So with that, what you'll find in textbooks for polyprotic acids are multiple Ka values. So Ka1, Ka2, Ka3 to represent, how acidic is that first proton? How acidic is the second one? How acidic is the third one? The first proton's always going to be the most acidic. It's the one that's going to pop off the easiest. As you start to take off subsequent protons, they become less and less acidic. So here's some example of polyprotic acids. Like ascorbic acid has 2 protons. You can see it in its formula, so that's why you see a Ka1 value and a Ka2 value. Notice how the Ka1 value is always greater, is a bigger number than Ka2, which is always greater than Ka3. That's what I mean, that the first proton is the most acidic, the last proton is the least acidic. Or let's look at a triprotic acid, phosphoric acid, H3PO4. There's your first proton, second proton, third proton, right? So let's look at the, and I'll point out here a small detail that sulfuric acid, we learned that sulfuric acid was a strong acid back in 1210. But a small detail that, you might have missed in 1210 is when we said that sulfuric acid was a strong acid, we only meant the first proton. All right, the first proton in sulfuric acid is a strong acid. It fully ionizes. But once you take off that first proton in sulfuric acid, you make HSO4 minus. This is called bisulfate ion. Bisulfate, HSO4 minus. That proton is actually a weak acid. So you see that in its K values. For sulfuric acid, the Ka1 is so large, there's no value. It's essentially an infinity because it's a strong acid. But notice the second proton. So the second proton is this proton in bisulfate, HSO4 minus, does have a Ka value. All right, so HSO4 minus is actually a weak acid. So that's a small detail that in 1210 we kind of glossed over, but in this class we'll go into more detail. Okay, so let's write the equations describing Ka1, Ka2, Ka3 for phosphoric acid. So again, these protons, they pop off one at a time. So Ka1 represents that first proton popping off. So you want to start with so the equation, you want to start with the fully protonated form, so H3PO4, aqueous. We want to only take off one proton. So notice how this is going to match the exact same weak acid equation that we've been working with before. HA becomes H plus and A minus, where only the first proton comes off, so you get H plus, and that's aqueous. And the other thing that's left behind is H2 PO4 minus, aqueous. So notice how it is atom balanced and it is charge balanced. So that's the first proton coming off. But there's two more protons, so that's why we have a Ka2 and Ka3. So the strategy here is, okay, take that product in Ka1. We're going to take that product and it's going to become the reactant in the next Ka expression because I popped off that first proton. Now let's take off the second proton, but now this thing is your reactant. You're not going to start with H3PO4 because in order to take off the second proton, you have to take off the first one before then. So H2PO4 minus is going to become the reactant in Ka2. So this is H2PO4 minus. Now this thing is going to act as an acid. So you're going to just pop off another proton and think what is left over. HPO4, but what's the charge? 2 minus, yeah. Okay. So then what do you think the reactant is in in Ka3? It is, again, the product of the previous one. So now in order to take off that third proton, you have to take off the first and second first. So our product now is HPO4 2 minus. This thing is going to act as an acid. It's going to pop off that H plus. But now what's left over is PO4 3 minus, aqueous. And so all of these expressions, all of these chemical equations have different K values. And so if you look at, let's actually give Ka values for all of these reactions we just drew. I'll get rid of these arrows. Here, I'll highlight that. So that goes there. This one goes here. So Ka1 for phosphoric acid, so there's that. I'm not going to write the full number. This is times 10 to the negative 3, times 10 to the negative 8, and this one's times 10 to the negative 13. So you can clearly see that the Ka1 value is the strongest acid of all of these K values. That first proton is the most acidic. So this first proton, because its Ka value is the largest, versus Ka3, that third proton times 10 to the negative 13, it's much, much harder to take that proton off. That this reaction does not go in the forward direction that much because that Ka3 value is so small, right? All right, so that's for a polyprotic acid. Okay, because some acids, yes, you can clearly see there's more than one proton that can be donated. Okay, so let's look at, weak bases now. Cool, so we just did acids. Let's remind ourselves about weak bases. Weak acids are always easier. Bases, on the other hand, always harder. Weak bases are harder. So let's review a generic weak base equation. Weak bases, Bronsted-Lowry bases, they accept protons. So when you write the equation here, notice that you have to have that water molecule present because that ammonia has to grab a proton from somewhere. It's going to grab it from water, and you get ammonium and the conjugate acid and hydroxide, where that came from water. So when we write the Kb expression for this, again, it is products over reactants. So NH3, whoops, nope, NH4, sorry, products over reactants. Water doesn't need to be in there, but it does need to be in the balanced equation. Okay. So there's our Kb expression. So we calculated the pH of a weak acid, used an ice table. So now it's time to use an ice table to calculate the pH of a weak base. Don't worry, it's the exact same strategy. Okay, so like before, remember ice tables, there's two types. There's the one where we fill in the ice table. It's the Sudoku method. We never make an approximation, or the one where we solve for x and make the approximation. So let's do type 1 first, where we never approximate. The reason we don't approximate is because I tell you the concentration and I tell you the pH and I ask you to calculate Kb. All right, so we're not solving for x. I'm kind of giving you x, a hint at what x is. And notice the wording of this question changed. This student prepared an ammonia solution and what? They measured its pH to be, yes, to be 11.13. So let's get it right this time. Okay, so same idea. Notice that we always did, for weak acids, we just did like our generic HA becomes H plus and A minus. For bases, it's a little bit different. We can also write a generic base equation where it's a little uglier, where you can call your weak base B, but the thing is you need a water molecule, and so that B weak base is still going to grab and steal a proton from water, making HB plus and hydroxide. So that's your generic Kb expression if you wanted to use that instead of the actual formula of the base that's there. So that'll always work for whatever base that you're working with, all right? So, okay, what information do we have? We have initial concentration. So in our ice table, we're going to put 0.1 molarity in for ammonia, zeros everywhere else. This reaction has to move in the forward direction, so minus x plus x plus x. Doesn't this look familiar? At equilibrium, it's 0.1 minus x, x, x. So I give you the Kb expression already. It's products over reactants. So we see that Kb is equal to x squared over 0.1 minus x. But here, we are solving for Kb. I didn't give you Kb. So the last piece of information I gave you is the pH. pH equals 11.13. Right? But so I give you the pH, so obviously we need to undo that pH to get a concentration. But if I do 10 to the negative pH, what comes out? The concentration of what? H plus. Is that what we want? No, what do we want? OH minus. X is the concentration of OH minus. So what do we have to do to that pH first? Probably. Turn it into POH. Yeah, so what we want to do is recognize, okay, pH represents the H plus concentration. But I need POH because that represents the hydroxide concentration. That is the value of X that I need in that ice table, all right? So let's just write out this work. So if pH is 11.13, that means POH is something. Did I write it down? Did I write it down? I don't know. 2.87. And that's the number that we use. So 10 to the negative POH tells me the OH minus concentration, and that is equal to X. So that number is equal to 0.00135 molarity hydroxide. And that is what X is. right? So weak base, it's literally the exact same process. It's just you need to inspect your ice table and make sure that you use the correct value of X, that we couldn't just do 10 to the negative pH because that gives us H plus concentration. Ammonia is a base. We used a Kb expression, so X represents hydroxide concentration. All right, so I'm going to shove this number back into the Kb expression. Should I approximate? No, because if you do approximate, you are just being lazy. Yeah, so just put in that X value as is. So it's 0.00135 squared over 0.1 minus 0.00135. Okay, and then you get a Kb value of 1.85 times 10 to the negative 5. Right, and that's like a normal Ka or Kb value. It's like 10 to the negative something. All right, so this was no different than the weak acid one. It's just we used a Kb expression. X represents hydroxide concentration. So keep that in mind because the next type of ice table is one where we do approximate. So this time I give you the Ka value, or sorry, we're doing bases. So Kb value. I give you Kb, 1.8 times 10 to the negative 5 for ammonia. And I ask you, what is the pH of this concentration, 0.3 molarity ammonia solution? So same idea. Write out your ice table. Here's our Kb expression. Again, you can also just use the generic form of a weak base equation. So base plus a water gets you Hb plus, that's your conjugate acid, hydroxide. I'm going to point out weak bases are always harder to do than weak acids. Weak acids are a lot more straightforward. It's HA, it splits up into H plus and A minus, sure. But base is a little bit trickier. So same idea, we plug in that concentration, so different color, come on. 0.3 molarity for ammonia, zeros everywhere else, minus X, plus X, plus X. Are you getting bored of this yet? Yeah. 0.3 minus X, X, X. Perfect. We literally did the exact same question, I think now 6 times in a row, right? The same ice table. But then that E line goes into Kb. And so remember that I'll write the generic form of the Kb expression. So here I have it for specifically ammonia, but for a generic base, it would just be Hb plus over hydroxide concentration over base concentration. That's for a generic one, all right? But notice here that because this is Kb, see how hydroxide is in the numerator? In a Ka expression, H plus is in the numerator because it is a different equation, right? Just like all ice tables, shove that E line into the Kb expression. So Kb equals X squared over 0.3 minus X. And I tell you, Kb is 1.8 times 10 to the negative 5. You can solve that with the quadratic if you want. Do you want? No. So let's approximate. So let's get rid of that minus X, and this simplifies into X squared over 0.3 equals 1.8 times 10 to the negative 5. So then all you need to do, calculate X, you just take a square root. So multiply those two numbers together, take the square root, we get X is equal to 0.00232 molarity. But X represents the molarity of what? OH minus. How did you know that? From the ice table, yes. Also, here's the hint. If it's a Kb expression, B stands for base. X is hydroxide. Ka expressions, Ka stands for acid. X represents H plus, all right? So you don't really have to do an ice table every single time, but I encourage you to do it, like do it for homework, and then you'll see the patterns come out. All right, so yes, that is the concentration of hydroxide. So when you negative log that, you are calculating POH, and then just you're one step away from getting pH. So that means our POH is equal to 2.63. So you know if this was a multiple choice question, 2.63 would be an option. But what did you put into water? A base. Is that a basic pH? No. That's because you calculated pOH. So to get pH, it's 14 minus, so it's 11.37, and that is much more reasonable for adding a base. Do you like these kinds of ice tables? These ones are fun because it's always 1-to-1. They always look the same. You can always approximate. It's great. And of course, if we wanted to calculate the percent ionization, same idea. Just do X over the initial concentration times 100. That's percent ionization as well. All right, okay. Those are our weak bases. So the reason bases are harder to distinguish is because it's not so obvious what bases look like. Ammonia. I don't see a hydroxide anywhere in ammonia, but where the hydroxide comes from is when it reacts with water. So the reason weak bases are harder is because they're just harder to identify that it's even a weak base. So in this course, ammonia is not the only weak base anymore. Back in Chem 1210, we just told you, memorize ammonia as a weak base and be on your way. Versus like weak acids and strong acids, we just said memorize the 7 strong acids, everything else is a weak acid. That was a little easier. But we're going to learn more about a lot of the other types of weak bases that are out there. There's 2 main types of weak bases. And so the ones that you want to be looking out for are neutral substances that have a nitrogen attached to it somewhere. So I like to call these like, they look like ammonia. They look like ammonia. As long as you memorize that ammonia is a weak base, if it looks like ammonia and there's a nitrogen on it and it's charge neutral, it's probably a weak base. So if you look at like these top 4, so look at these top 4. We got ammonia, pyridine, hydroxylamine, methylamine. See how all of them look like ammonia because they have an N with a lone pair, N with a lone pair, N with a lone pair, N with a lone pair. They all look like ammonia. They're all weak bases. They all have Kb values associated with them, right? And same thing with weak bases. If the Kb is a larger number, then it's a stronger base than something with a smaller Kb. All right, so that's the one you want to look for. But then what we're going to learn about here, remember when we talked about weak acids? The stronger the weak acid, the crappier its conjugate base. So if you have HA, that's an acid. A minus is actually a weak base. All right, so there's another kind of class of weak bases that we can have. It can be a conjugate of an acid. HF is a weak acid, but F minus is also a weak base. So there's another class of weak bases we're going to talk about. All right, so oh yeah, here's an example. So if HA, a weak acid, HF's a weak acid, but A minus or F minus is actually a weak base, right? And so that's where things get a little complicated now, where Ka for an HA weak acid, it's pretty straightforward to calculate the pH. Or if I have ammonia, a base, I use its Kb, we can also calculate the pHs of conjugates, and that's what we're going to move on to now. I'll note here that okay, like you can go to the store and buy HF in a bottle. But if you want to go to the store and buy its conjugate base, F minus, you can't just buy F minus at a store. The reason is because F minus is an anion. You can't just buy the anion part. They always come in a cation-anion pair. You can't just get one of them. So what's oftentimes difficult, and I think this is one of your labs, is identifying, well, what part of this is basic and how do I get it off the shelf? So if you wanted F minus, the conjugate base, you would have to grab from the shelf NaF. You have to buy the cation-anion pair that includes that conjugate base that you want. Because everything, all salts, when we get them off the shelf, if we buy them from Amazon, have to be a charge neutral salt. So F minus is in here, but it has to exist as an ionic salt. Yeah, so if you wanted to add carbonate in a reaction, you're not going to grab carbonate ion from the shelf. You will never find that. You actually have to look for sodium carbonate because what happens here is that sodium is a countercation that's charged, that's pH neutral, so it doesn't interfere with like your reaction. It acts as a spectator ion. So keep that in mind. We'll be looking at acidic basic properties of salts here soon. Okay. All right. Okay, so those are some weak bases. Okay, yeah, and so again, the weak bases that we're going to be looking at, most of them that are charge neutral, they look like ammonia. They look like ammonia. So here are 4 different examples. Ammonia looks like this. Nitrogen with 3 hydrogens on it, there's the lone pair. There's its conjugate acid, ammonium. It has 4 H pluses because it grabbed, accepted a proton from water, but now it's a positive charge. Okay, so that's ammonia, 3 hydrogens. So I like to think a lot of the weak bases that we see that are ammonia-like look like ammonia. It's just we're replacing those hydrogens with other things. So methylamine, this is typically what you'll see on paper. Squint your eyes. CH3NH2. This looks like ammonia. Just squint your eyes because ammonia is NH3. So essentially when we make methylamine, we're just changing one of those hydrogens to a methyl group instead. So basically you take an ammonia, replace one of those hydrogens. I'll do this in a different color. Come on, different color. I'm replacing one of those hydrogens with a methyl group instead, CH3, right? So then when I write out the conjugate acid, CH3, but remember that conjugate acid has an extra proton on it, so you have a hydrogen up there and a positive charge. So notice how all of these basically look the same. It's just, you're just changing the hydrogens on the outside of ammonia. Or here, that was methylamine. Here's another example of a weak base, dimethylamine. It looks like ammonia, but what we're doing here is we're just changing both of these 2 hydrogens on the sides of ammonia to methyl groups instead. So to make the conjugate acid, that lone pair is just going to grab a proton, essentially. And so if I draw that out, we have those 2 methyl groups are still there, but instead of a lone pair, we have an extra proton on the top there, and it's overall positive charge. Look how all of these look very similar. So we got methylamine, dimethylamine. Now ethylamine, notice this is what you're going to find on paper. We don't like draw out the full formula or anything. Ethylamine, squint your eyes. It looks like ammonia with some just spaghetti like attached to it, where one of those hydrogens now has just a 2 carbon chain instead of that hydrogen. So this is CH2, CH3. Here we go. So it just has this carbon chain attached to it. So if we wanted to make the conjugate acid, we still have that carbon chain attached to it. Or I don't feel like writing the hydrogens. But then that lone pair is converted to that proton that got accepted to make that conjugate acid. When that base acts like a Bronson-Lowry base, it accepts a proton and becomes the conjugate acid. So all of these, when you squint your eyes, they all look like ammonia. And that's the hardest part of weak bases, is you read the formula and you go, what the heck is that? Well, it looks like ammonia, so it's probably going to act like a weak base. Okay, so hopefully this is where it all comes together, right? The relationship between Ka and Kb for a conjugate acid-base pair. Remember, HF is an acid. F minus is its conjugate base, so F minus acts like a base. Or ammonia is a weak base. Its conjugate acid is NH4+. NH4+ is an acid because it's the conjugate acid, right? So let's see how this ammonia-ammonium conjugate acid-base pair behaves. So let's go through this. Let's write the equilibrium describing ammonia acting like a base. So let's write the Kb expression for ammonia acting like a base. So bases accept protons. So this ammonia is going to grab one of those protons off of water to make NH4+. It's aqueous. I just don't feel like writing it. And what's left over is hydroxide. That's a generic Kb expression. All right? So that's ammonia. Now let's describe ammonium, its conjugate acid acting like an acid. Acids, you can, again, just think of this as HA, all right? So when ammonium acts as an acid, it donates one of its protons. So if I rip off a proton off of NH4+, what is left behind? So rip off a hydrogen, so now we go from H4 to H3, but then how does the charge change? Now it is charge neutral. All right. So that is the Ka expression for ammonium acting like an acid. For a long time when I was in Gen Chem, I always thought Kas and Kbs were reverses of one another. They are not. A Ka is your thing is acting as an acid, so it donates a proton. A Kb is your thing is acting like a base, so it accepts a proton, and typically what's also given off is a hydroxide from water. Kas and Kbs are not reverses of one another. All right, so what's special about these two reactions, because I wrote a Ka and Kb for a conjugate acid-base pair, for funsies, add those two reactions up. Okay, what cancels? What cancels? Doesn't this cancel? Ammonium cancel? What else cancels? NH3. And then what's left behind? Water, so H2O, liquid, arrow, and then our two products are H plus and hydroxide. Is that a K expression we know? Do we already know that one? Yeah, what is that? K, W. W stands for water. And so look, we got water and its self-ionization come out of this. So the beauty, what we just proved, okay? What we just proved is for a conjugate acid-base pair, the Ka for the acid and the Kb for the base form, when you multiply those two things together, you get Kw, right? So that means if I give you the Ka for HF, you actually already know. If you know what that number is, if I tell you like Ka is 1 times 10 to the negative 4 or something, if you wanted the Kb for F minus, you just have to use Kw to get it, all right? That Kb for F minus is simply going to be Kw, which is already a number you know. It's 1 times 10 to the negative 14 over the Ka that you know, right? So that's how all of this comes together. And mathematically, why weak acids, like really crappy weak acids, have really strong conjugate bases. And we'll look at some examples in a minute. Okay, so yeah, for a conjugate acid-base pair, so Ha and A minus, or ammonia, B and HB plus, the Kas and Kbs for a conjugate acid-base pair are related by Kw. That is super, super important, okay? And why this is important is because we, in the previous sections, we just put Ha, a weak acid, into solution, or we put B, a base, weak base, into solution. But couldn't we also put, instead of like HF, we could put NaF into water instead. But here's the thing, if I put NaF into water, the calculation changes. Ha is an acid. You use Ka to calculate the pH. But A minus is a base, right? So that means you have to use Kb to calculate the base, or calculate the pH for that base. But you get that Kb for A minus from the Ka that's already known for Ha. Because you'll find Ha in the book, but you won't find A minus in the book. So you have to calculate it yourself. So here, Kb is equal to Kw over Ka. You know Ka, you know Kw, so you just have to kind of futz around to get what Kb is if you put A minus into solution. So some examples of A minus. Okay, you can calculate the pH of an HF solution if I give you Ka, but you have to use Kb if you put F minus into solution. If F minus is present, then you have to use Kb instead. Or here, this is acetic acid, HCH3COO. That's a weak acid. But if you put acetate, CH3COO minus, into solution, that is a weak base. So you have to use Kb. This is nitrous acid. Nitrous acid is an acid. You use Ka. But if you put NO2 minus in solution, that's its conjugate base. You actually have to use Kb, right? So it's being able to identify, am I looking at an acid or am I looking at its conjugate? All right, and that's like the whole idea between, when do you do SAL, the SAL lab? Or SO, yeah, SAL. Tomorrow or Thursday? Tuesday, next week. What is today, Friday? Okay, all right, so next week, all right, you'll be doing this. Basically looking at acids and their conjugate bases, or bases and their conjugate acids. and how we interpret those. Okay, so those are for acids. Bases, same idea. B, like ammonia, is a base. You use Kb to calculate the pH. But if you put NH4 plus into water, that's an acid. So you have to use the Ka. But you get the Ka by just calculating it. It's Kw over Kb. Right? That's the relationship. But it's reading the formula and understand, what am I looking at? Am I looking at the base or the conjugate acid? And that's the hard part. Or here, this is methylamine. Okay, so methylamine, you use Kb because it's a base. But if you see CH3, NH3 plus, that's its conjugate acid. So you use Ka, right? Or here, this is pyridine, C5H5N. That's a base, so you use Kb. But if you put into solution pyridinium, C5H5NH plus, that's an acid, so you have to use Ka. But of course, you calculate Ka by using the given Kb for the neutral base form. All right? And so what we see here at the bottom here, okay? So for funsies, if like I have an acid, HA, and I tell you its Ka is 1 times 10 to the negative 4. What is the Kb for A minus? So remember how we make the relationship between Ka times Kb equals Kw. So that means Kb for A minus, that generic acid, is Kw over Ka. So Kw over Ka is 1 times 10 to the negative 14. And if I tell you Ka is 1 times 10 to the negative 4, if you do this math in your calculator, and hopefully you'll do it enough that you just see how dividing exponents work, you'll see that Kb is equal to 1 times 10 to the negative 10. Right? So basically it's the difference of the exponents. Right? So for A minus, Kb is 1 times 10 to the negative 10. So look here. Ka and Kw for a conjugate acid-base pair are related to one another. So the larger Ka is, the smaller Kw or Kb is for its conjugate base. And it's because both of those numbers have to multiply to give you Kw. And so that's where that whole, you know, the mantra that we followed, the stronger the acid, the crappier the base, is because of this reason. The larger the Ka value, the smaller the Kb value for its conjugate base. Or a crappy acid has what kind of Ka value, big or small? Small. So if you have a really crappy acid, what is the behavior of its conjugate base? It's really strong. And what kind of Kb value will you find? A really big one, yes. And it's all based upon math and this idea Ka and Kb are related to Kw. Okay. Great, 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 great. All right, so let's do some calculations. But don't be scared. It's just like before. We always approximate. It's just what do we use? Okay, so here, what is the pH? So this is a type 2 ice table. It's going to be x squared over something equals some K value. What is the pH of a 0.3 molarity ammonium chloride solution? Right, so we're going to do an ice table. We're going to do x squared over initial concentration, but the question is equal to what? Right, so we need to ask ourselves, when you put ammonium chloride into solution, that's a salt, all right? It has a cation and an anion. So what you want to do is separate the cation and anion and look at them separately. So ammonium, this is NH4 plus, and then chloride, Cl minus. So you need to ask yourself, does this salt act like an acid or a base? That answer will tell you what K value to use. So look at them individually. Ammonium is a what? It's an acid. How do you know? It's the conjugate of a weak base, all right? NH4 plus is an acid because ammonia is a base, is a weak base, I should say, weak base, right? That's why. Chloride, though, is, I'm just going to tell you right now, is a pH neutral salt. I'll tell you why later. Okay. The reason is because HCl is a strong acid. That's why. Okay. all right? So that means if you put ammonium chloride in water, you have a component that is acidic and something that's pH neutral. So the whole solution should be acidic, right? So what K should we use? Ka. And that's what we're going to do. We're going to use Ka. But did I give you Ka? Did I give you Ka? Oh, is this just a mistake? No, it's not a mistake, all right? We need to use Ka for ammonium, right? We need to use Ka for NH4+. I didn't give you that. I gave you a Kb for ammonia, but no worries. You know how to calculate Ka. Ka is simply Kw over the Kb that's given. You know Kw and Kb is given for ammonia. So simply the Ka for ammonium is 1 times 10 to the negative 14 over the Kb that's given, 1.8 times 10 to the negative 5. So Ka for ammonium is 5.56 times 10 to the negative 10. That is Ka. That's the number that we're going to use in our ice table. All right, so since we're using a Ka, we're going to use a Ka expression. So Ha breaks up into H plus and A minus. Again, you can use the generic form. It works out the same. It's NH4 plus breaks up into H plus and ammonia. That's like the actual reaction that's happening, but we can use the generic form as well. We write out our ice table, just like always. Initially, we have 0.3 of ammonium, minus X plus X plus X, right? And so then we get at equilibrium, it's 0.3 minus X, X, X. And so when we shove that into our Ka expression, it becomes x squared over 0.3 minus x equals that 5.56 times 10 to the negative 10 value we got before. Are we going to approximate? Heck yes, we are. Yes, we are. So we're going to get rid of that minus x. And then we'll get what x is. X is equal to, so just take the square root. It's something like 1.3 times 10 to the negative 5 molarity. But it's molarity of what? H plus, yes. How do we know? Because we use the Ka expression. And in a Ka, X is equal to H plus concentration. We could see it in the ice table. All right? So there's X. We're just one step away to getting pH. All right? So you might be asking, how is this any different than the 6 that we've done before? The only difference is we had to do this step right here to get the Ka, because I didn't give you the Ka directly. Because ammonium, NH4+, you're not going to find the Ka in a book. You're going to find the Kb of ammonia, the charge neutral NH3 version in the book, right? So it's identifying conjugates, and that's the section we're on, identifying conjugates. Okay, keep going. All right, another one. Same idea. Do we use Ka or Kb? Obviously, it's a pH calculation, so it's going to be x squared over initial concentration. I'm not even going to write the ice table anymore, all right? Okay, it's x squared over 0.3 equals something. But what is that something and what is X? So we are putting sodium cyanide into solution. So we have Na plus and Cn minus in solution. So we need to ask ourselves, is that going to act like an acid or a base? Na plus is a pH neutral salt because sodium hydroxide is a strong base. So I'm just going to tell you that, strong base, right? But Cn minus is a what? It is a base, yeah, it is a base. But why? Because HCN is a weak acid. How the heck do I know that HCN is a weak acid? Well, the hint is, look, I give you a Ka for HCN right there, right? But here's the thing, did you put HCN into water? Nope, you put its conjugate base in. So what kind of K expression do you want to use? Kb. But I didn't give you Kb, but that's okay because we can just calculate it. So that means this, when we do the ice table and we make the approximation, it's going to end up being x squared over 0.3. But we're going to set this equal to Kb because Cn minus is a base. I didn't give you Kb. I gave you Ka. That's not a mistake. It wasn't a typo on my part. You have to calculate Kb by taking Kw over Ka, the things you do know. And so putting this all together, it's going to be x squared over 0.3 equals 1 times 10 to the negative 14 over Ka, which was given 4.9 times 10 to the negative 10. All right, you can solve that. I already did the approximation, and you get that x is equal to, I don't know, 0.00232 molarity. But it's the molarity of what? Ooh, there's no ice table to help you. But what kind of K expression did you use? Kb, because Cn minus is a weak base. So that means X is the concentration of hydroxide. Yeah. All right, so that means you calculate POH first. POH is equal to 2.63, and then you get a pH of 11.39. And that's really satisfying because what did you put into water? A weak base. So the pH should be basic. In the previous question, what did we put into water? A weak acid. We got an acidic pH. Fantastic. All right. So these are the harder ones. They're harder because I'm not giving you the acid, the Ka, Kb straight up. You have to recognize, oh, you're looking at the conjugate. How do I adjust that to make the appropriate ice table? Okay. All right. Let's keep going. All right. Let's do one more. What's in my beaker? An acid, a base. What do I use? So let's put pyridinium chloride into water. Cl minus is pH neutral. But what the heck is this thing? What the heck is that thing? It's an acid, yes. It is ammonia with a H plus on it, okay? It looks just like ammonia. Just squint your eyes. There's a nitrogen thing. There's a plus sign on it. So it already gained that proton. So that is an acid. So I want to use a Ka expression, right? But if you look at this, did I give you the Ka of pyridine? Nope, I gave you this 1.7 times 10 to the negative 9. That is Kb, not Ka. All right, so that means Ka for pyridinium is equal to Kw over Kb. Can you tell me without doing the ice table, Ka is equal to what after the ice table? X squared over 0.1. Minus X, but I'm just going to approximate right away, right? So see how the concentration is that. And so we're going to calculate the pH, so we need to calculate what X is. And so X squared over 0.1 equals 1 times 10 to the negative 14 over 1 times 1.7 times 10 to the negative 9. So we can solve that. I've already approximated. I skipped the ice table because we've done like 8 of them already. Hold on. Was this answer, I don't know, was this answer right? This number might not have been right, I'm sorry. And this number wasn't right. I was looking at the wrong part of my key. This number is 0.0025 molarity. It's just a little bit off. And this is 2.61. There we go. All right, sorry about that. This one, X is equal to, well, Ka, if we do this, is equal to 7.7 times 10 to the negative 4 molarity. And so if you solve for X, it's no, it's not. Oh my gosh, I'm getting all my numbers mixed up. Ka is equal to 5.9 times 10 to the negative 6. See how that's different than the Kb that's given in the question. If you solve for X by taking the square root, it's 7.7 times 10 to the negative 4 molarity. But it's molarity of what? H plus. Yes, it is H plus because we used Ka. And so you just go ahead and negative log and you get a pH of 3-ish. Perfect, because that's, you put a weak acid into solution. So the pH that should come out should be acidic. Okay. All right, so let's do, all right, yeah, so those are the conjugates. So let's put that all together. So that's the mathematical part, using Ka, Kb's, and all of that. So this next part should help you with your lab for SAL next Tuesday. So remember, you don't have to put HA, a weak acid, in solution. You can put A minus. If HA is a weak acid, A minus is a weak base, right? If B is a weak base, if you put HB plus into water, it is a weak acid, right? So when we look at conjugates, so like A minus, HB plus, notice how they're cations and anions. So salts typically have different behaviors that we have to kind of think about in this like backwards manner. HA is already charge neutral, it's an acid, but A minus is an anion. B is already charge neutral, but HB plus is a cation. So what we see here is when we put salts in solution, they are charge neutral, and we can identify, are these salts overall acidic or basic? So this is kind of more the conceptual part of this chapter. And it's just being able to recognize, okay, I'm giving you a salt like NaCl. Tell me, is it acidic, basic, or neutral if I put it into water? And we'll do some demos and see. So here's the strategy. For any salt like MX, where M is a cation, X is an anion, you want to look at them separately. The M part, the cation part, if the thing is an acid, it's going to show up in the cation spot, right? The reason is this statement up here. These are our salts. A minus, those are conjugate bases, but HB pluses, those are our conjugate acids. So if your salt is an acid, it's going to show up in the cation spot. But it's only going to act like an acid if that cation is the conjugate of a weak base. If it's the conjugate of a strong base, then it's actually pH neutral. So remember, the weaker the base, the stronger its conjugate acid. So if you have a really strong base, its conjugate is going to be the worst acid in the world. It's going to be pH neutral, right? So that's what we want to think about here, right? Cations. Typically, they're acids because they're conjugates of weak bases, but also another class of acidic cations are Lewis acids. So very small, highly charged cations like iron 3+, silver+, and like aluminum 3+. Those types of really small cations act as Lewis acids that we talked about a little bit earlier, right? On the other hand, anions, if you have an anion in your salts and you inspect it, if that thing is a base, it's going to show up in the anion spot because conjugates of weak acids are typically negatively charged. So things like carbonate, F-, acetate, all of those are conjugates of weak acids. So if you see those, they're going to act like weak bases, all right? But things to look out for are pH neutral things. All right, so you can have a salt like Na+, cation. Na+ is a pH neutral salt, so it's pH 7, so essentially you ignore it. And the reason is because sodium hydroxide is a strong base. Or anions from strong acids are also pH neutral, such as nitrate, chloride, those types of things. All right, so anything originating from a strong acid or base is going to be pH neutral, but anything originating from a weak acid or base is going to have a also weak conjugate. So that's what we want to look out for. One exception is sulfate. Remember, there's 6 or 7 strong acids. Sulfuric acid is one of them, but because it's polyprotic and only the first proton is strong and the second proton is a weak acid, this thing is not pH neutral. All the rest are, it's just not sulfate. Okay, all right, okay, so, oh yeah, here we go. So let me just clarify those Lewis acids that I mentioned, that cations can either be acidic if it's a conjugate of a weak base or if it's a Lewis acid. So an example would be iron 3+. So Lewis acids do what? or Lewis acids and bases, what are we focusing on? Are we focusing on protons? Nope, we're focusing on electrons. Yes, so Lewis bases donate electrons. Lewis acids accept electrons. So notice iron 3+ is a good Lewis acid. The reason is because it's highly charged. It's very, very positively charged. Electrons are very attracted to positively charged things. So what we see here are that oftentimes Lewis acids here are very highly charged cations that are not group 1 or group 2. So what we see here is all of these cations have, slightly elevated Ka values, meaning they are slightly acidic. The trends are with acidity with Lewis acids is the tighter that charge density. So if you have like a really positive charge localized in one small spot, it's going to attract electrons a lot more. It's going to work better as a Lewis acid. So the trends are that Ka increases, your cation becomes more acidic if your charge increases, so +1, +2, +3. +3 is going to be the most acidic, but also if you have a really small size. So essentially with these two trends, we're increasing charge density. So things like iron, nickel, chromium, aluminum, even silver, all of those are Lewis acids, versus things like sodium plus, potassium plus, calcium 2+. All of these are pH neutral. Because the rule is pH neutral cations are all group 1A and 2A cations. But basically anything else that's not a group 1A or 2A cation is going to be a Lewis acid. Okay, great, great. Okay, all right. So let's do this and then do the demo. So here's a bunch of formulas. Let's look. Are these salts, when you dissolve them in water, are they going to be acidic, basic, or neutral? So let's go through them one by one. This is the strategy you want to do. So this is an overall salt. So that means we have a cation and an anion. Separate them and look at them separately. So when you dissolve ammonium nitrate into water, you get an NH4+ cation and an NO3- anion. So we look at those separately. Ammonium is going to act like a what? Acid. Why? This is going to be acidic because NH3 is a weak base, right? So ammonium is the conjugate acid of a weak base, ammonia. So this is acidic. But what about nitrate? What is that going to be? This is going to be charge neutral, pH 7, because HNO3, nitric acid, is a strong acid. So nitric acid is the acid, nitrate is the conjugate. Very, very strong acids have really crappy bases. So nitrate is so bad of a base, it's not even a base, it's just charge, it's just pH neutral, right? So what should our solution behave like if I combine something that's acidic and neutral? Acidic, yeah. So this will be overall acidic. All right, let's keep going. NaF. So you put that into water. You get sodium plus and F minus. We look at them separately. Sodium plus is going to behave how? This is going to be neutral. Once you see sodium like a bunch of times, you'll know that it's always going to be neutral. And the reason is because sodium hydroxide is a strong base. A strong base has a very, very crappy conjugate. So that means Na plus is so crappy of an acid, it is charge neutral. Or sorry, not charge neutral, pH neutral. Versus F minus, what is that going to act like? That, so here, think about it this way. When we look at salts, we're always looking at the conjugate. So just undo the conjugate. F minus is the conjugate of what? HF. Then you ask yourself, what kind of thing is HF? This is a weak acid. So therefore, F minus is a weak base. So this whole substance, NaF, is going to act how? Basic. Because F minus is a weak base. You can ignore sodium plus because it's charge neutral, or pH neutral, sorry. All right, KBr. We got K plus and Br minus. K plus is the conjugate of KOH. Br minus is the conjugate of HBr. KOH is a strong base. So K plus is a neutral. It is nothing. HBr is a strong acid. So Br minus is a nothing, or a neutral. It's neutral. So that means we combine two things that are pH neutral. What should KBr behave like? The actual salt. It should be neutral. Yeah, so it should not change your pH at all because both things are neutral. All right, keep going. Na2CO3. So we put two equivalences of sodium plus, and then we have an equivalence of carbonate. So Na plus is going to be pH what? Neutral. We've seen it enough now, I think, I hope. Okay, and again, it's because sodium hydroxide is a strong base. All right, carbonate. This one's tricky. Carbonate is the conjugate of HCO3 or H2CO3, carbonic acid. Carbonic acid is a weak acid. So that means carbonate is going to be a weak base. Yes, it's going to be a weak base. So this whole thing, it's going to be basic because you got something neutral and something basic. All right, keep going. KCN, K plus, CN minus. K plus is pH neutral because it comes from KOH, which is a strong base. But CN minus comes from HCN, which is a weak acid. So therefore, CN minus is a base. So that means this whole thing's going to be basic. All right. See, no math at all except kind of understanding and memorizing what's a strong base and strong acid. And basically everything else is going to be a weak acid or weak base. So here we have aluminum chloride. So we have Al3 plus and Cl minus. Chloride comes from HCl. So that means Cl minus is what? Neutral. Yes, it is neutral. What about Al3 plus? This one's tricky because we were always looking at conjugates. We were always looking for weak things. But Al3 plus is special because this is a Lewis acid. It is a highly charged non-group 1 or 2 cation. So that's like the one that's like different. It's like the weird wrench that's thrown in there. So here we see Al3 plus is a Lewis acid. So this whole thing is acidic because of aluminum 3 plus, because it's a highly charged cation on that previous slide. Okay, Ki. We got K plus, I minus. K plus comes from KOH. I minus comes from HI. So tell me, you put Ki into water, how should the pH change or not? It should say the same. It's going to be neutral, and it's because both of these KOH and HI are strong acids and bases. So that means their conjugates are nothing. They're pH nothing. All right, this one's harder. You put this into water, you get ammonium, and you get fluoride. Ammonium comes from NH3. Fluoride comes from HF. So ammonium acts like a what? Weak acid. F minus acts like a weak base. Yikes. So then what is this? You might think, oh, it's neutral. But not necessarily, because how good of an acid is ammonium? How good of a base is F minus? So we can't actually solve this question unless I give you K values, which I have down there in the corner, okay? So you put into water NH4 plus and F minus, but are those the K values I gave you? No, I gave you the Ka of HF and the Kb of ammonium. So I need to compare what is the Ka value of ammonium, and I need to compare it to the Kb value of F minus. But we can just simply look at these numbers and calculate it. Remember that Ka equals Kw over Kb. I give you the Kb of ammonia. It's 1.8 times 10 to the negative 5. I'm just going to look at the exponents here because all I need to do is know which one's bigger. I don't need to actually calculate it. So Ka for ammonium is going to be 1 times 10 to the negative 14 over 1 times 10 to the negative 5. So this is equal to times 10 to the negative 9. All right, that's Ka for ammonium. I just need to know magnitudes. So I'm just looking at the exponents. I'm not actually calculating it. So to calculate Kb of F minus, we take Kw over Ka. Because I didn't give you Kb of F minus, I gave you the Ka of HF. So simply Kb here for F minus is going to be 10 to the negative 14 over 10 to the negative 4. So Kb for F minus is equal to what? 10 to the negative 10. So which one wins? What number is bigger, Ka or Kb? Ka, yes. So this thing is going to be what? Acidic. It's going to be acidic because Ka is larger than Kb. Right? And the only way we could have solved this is if I gave you K values. Right? But again, you're comparing the Ks of the conjugates, not the actual stuff. Okay, so let's do a demo and go through the same thing. Are these salts going to be acidic, basic, or neutral? So I got my indicator here. Let's remind ourselves what acidic, basic, and neutral looks like. So here I have my neutral reference. It's green. This is pH 7. Let me put a drop of sodium hydroxide in one of them. Sodium hydroxide should make the solution basic. Yes, so this is what basic looks like. Let's mix you up. Okay, that's basic. And then I'm going to put a drop of HCl in this one. HCl is hydrochloric acid, so it's going to make this solution acidic. Yeah, so this is what acidic looks like. I can probably use the same thing. There you go. All right. So this will help reference ourselves to what these salts are. So what's the first one we're going to do? Let's do sodium nitrate. So sodium plus is what kind of salt? Cation. It's going to be pH neutral. What about nitrate? So nitrate is the conjugate of nitric acid, which is what kind of acid? Strong. So both things come from strong things. So the conjugates are going to be what? pH neutral. Yes, because everything comes from strong. So this one is sodium nitrate. So I'm going to just put a bunch in. And then we should hopefully not see a color change. It didn't change that much. Oh no, this was sodium nitrite. Crap. I read it wrong. Okay, so let's back it up. This was supposed to be sodium nitrite. I'm sorry. Yes, this one would have been pH neutral. It would have stayed green. But what I actually had in my hand was NaNO2. I know. So Na plus, still pH neutral. But what about nitrite? Nitrite is the conjugate of nitrous acid. What kind of acid is nitrous acid? It's not strong. Nitric acid is strong. Nitrous acid is weak. It's not one of the 7 strongs. Yeah, so that means nitrite, since it's the conjugate of a weak acid, is actually a weak base. So that's why this one turned kind of green. It just turned a little bit greener, closer to this blue color. So that's why this one turned blue, because I had sodium nitrite in my hand. Yeah, so this one, oh crap, where's my pen? Is, that one's, what did I just say? Basic. Okay, NaF. Sodium is going to be neutral. F minus, basic, because HF is a weak acid. So let's look at that. So NaF, let's see, sodium fluoride, it's going to be what? Basic. All right, so I'm going to put it right here. Okay, go. Okay. Is that basic? Yes, it is. It turned bluer. Okay, so there's that one. What's next? Ammonium nitrate. Okay, ammonium nitrate. So, ammonium nitrate, where are you? Ammonium Okay, ammonium nitrate. So nitrate is going to, the anion is going to be pH what? Neutral, because it comes from nitric acid. Oh, there's a lot of stuff going on here. It comes from nitric acid, but ammonium is the conjugate of what? Ammonia, which is a weak base, so that means ammonium is going to be acidic. So the whole salt is going to be acidic. Let's see. I don't know how, there we go. Is that acidic? Heck yeah, it is. So that was ammonium nitrate. All right, what's next? Silver nitrate. Silver nitrate. So which one can we just ignore right off the bat? Silver, yeah. Silver we can ignore because, or sorry, nitrate we can ignore because it's pH neutral. Crap, where are you? Silver nitrate. But the silver, this one's tricky. It's not a group 1 or 2 metal. It's actually a transition metal. So it is actually a Lewis acid. So silver, because it's highly charged, is going to, okay, we'll just put a big chunk in there, is going to accept electrons from water acting as a Lewis acid. So let's see. That changed a little bit, right? Got kind of orange. Yeah, so that one is not as acidic as like the previous ones we did, but it is a little bit acidic. Okay, next one. NaCl. Okay, sodium plus is going to be pH neutral because it comes from sodium hydroxide. Chloride, neutral because it comes from HCl. So what should this one do? It should do nothing. So hopefully it stays green. I think I've run out of like, oh wait, no, that's not right. That's not right. Ammonium chloride, sodium chloride, there it is. Okay, let's mix you up. So that's sodium chloride. Did it change? No, it did not. Okay, what's next? Aluminum chloride. So, which anion, or I already said it. The anion we can ignore. Chloride is pH neutral. We already saw chlorides are commonly pH neutral, but what about aluminum 3+? Acidic, because what kind of acid is it? It's a Lewis acid, yes. So this should turn orange. Oh yeah. Oh yeah, it turned orange. Whew, that is really acidic, wow. Okay, next one. What is that? Sodium choo-choo. It's acetate. So this is the conjugate base of acetic acid, which is a weak acid. So that means acetate is a weak. So acetic acid is a weak acid, so acetate is a weak base. Good. Why? I can ignore sodium plus because it is pH neutral. So I've run out of beakers. So this one is sodium acetate. It should be, what did we say? Basic, right? Basic. There we go. All right. And so that's the kind of conceptual type questions. They can either be quick, might be quick not even calculations, but being to identify, okay, we're looking at the cations and anions. What do they stem from? Weak acids or weak bases? But we're looking at the conjugates, all right? And so in all of these, at least one of the things ended up being neutral, so we could ignore it. If both your thing is an acid and the other thing is also a base, like a weak acid and a weak base, you have to compare the K values of those, all right? So we'll stop there. We'll finish chapter 16 on Monday and jump right into chapter 17. Just the first part of chapter 16 homework is due, all right? And I will post midterm grades right now, but I'll stay for like an extra 20 minutes because I feel bad that I didn't have office hours this week. So if you have questions about homework, I'll stay behind for a little bit.